Hi, welcome to Mechanical PE Exam Prep Question of the Week. This week I wanted to go over a very common question that comes up anytime you have air flowing over a coil. It's not always immediately obvious whether you should use the conditions entering the coil or the conditions leaving the coil to calculate different parameters such as what is the cooling load, what is the sensible cooling load, what is the sensible heat ratio. So I've cooked up this example to illustrate how different your answers might be depending on what choice you make. And another related question that comes up over and over again is, what about the rule of thumb 1.08 CFM delta T? When can you and can't you use that? How much error might you be introducing when you do? And I want to get into the detail, not that you should do this for every problem, but just to appreciate what's behind that rule of thumb so that when you use it, you know the level of risk that you're taking and what you need to look out for. Keep in mind this is just one example. I've set this up. You could certainly come up with some extreme conditions that would probably lead us to draw different conclusions, but this is a pretty typical case for a comfortable room and just a really classic air conditioning example. I'm not doing anything super interesting here, just cooling 76 degree air down to 55 degree air and maybe doing a little bit of latent there. But for the most part, this is a pretty classic air conditioning process. So let's start with the cooling load. Now we don't know right off the bat if there's any latent cooling happening. It could be purely sensible for all we know. But we do have the exact conditions of the entering air, let's call that state 1, and the exact conditions of the leaving air, that's state 2. We know two things about each state, so that's enough to fully define it. So let's see what that process line looks like on the psychrometric chart. I've already marked state 1 and state 2 based on the temperature and humidity, which we knew at state 1, and the temperature and wet bulb, which we knew at state 2. So from that we can gather these other values here, the enthalpy at state 1 and 2 and the specific volume at state 1 and 2. And we also noticed that this line is not purely horizontal to the left, so it's not purely sensible cooling. There is some latent cooling happening, which isn't totally surprising for the conditions that we had. So we should expect a sensible heat ratio that's less than 1, probably only slightly less than 1, but let's see how it plays out. So as far as picking these values, you can pick them directly off the chart. I put them into a psychrometric calculator to be extra precise for the sake of what we're trying to achieve here, which is understanding exactly how much error gets introduced by being a bit hand wavy in your assumptions. So I don't want to be hand wavy in the selection of those values off the chart, which is a pretty big source of error. If you're really rushing, you could round off and certainly introduce a couple of percent error just by picking the enthalpy without a really keen eye. So the enthalpy at state 1 is 28.74 BTU per pound, and the enthalpy at state 2 is 22.01 BTU per pound. And the specific volume at state 1 is 13.76 cubic feet per pound of dry air. I'm just going to write per pound for simplicity. And the specific volume at state 2 is 13.19 cubic feet per pound. So first of all, to answer the very common question that comes up, since we're given this volume, it's not obvious if they're referring to the volume of air entering the coil or the volume of air leaving the coil. Now the volume could actually change for a couple of reasons. One reason is that if there's any latent cooling happening, mass is actually being condensed out of the airstream. So the mass of dry air is constant, but the mass of water vapor as you go over the coil is less because some of that water vapor is dropping out. And the degree to which that affects the change varies depending on how much latent cooling is happening. The other effect that's happening is that the temperature is changing, and so the density is changing. And if you think of air as an ideal gas, you remember that PV equals nRT. So if you hold N and R constant, then as that temperature goes down for a constant pressure, because there's nothing really changing the pressure, the volume is going to go down as well. Now these effects are fairly minor because we're not making dramatic changes in the temperature, but it could be enough to affect the answer that we get. So we're going to use the conditions entering the coil. So we're going to use V1 anytime we have to express a mass flow rate when we're using this volume, and that's because this is the specific volume per pound of dry air, and the one thing that's conserved throughout this process is the mass flow rate of dry air. The volume can fluctuate based on PV-nRT, and the mass flow rate of water vapor can fluctuate due to latent cooling, but the mass flow rate of dry air is conserved. What enters the coil is what leaves the coil on a mass basis. So that's why we prefer to use the entering condition. So let's do some calculation. We'll say Q dot, and now when we say cooling load, we're referring to the total cooling load. So rather than consider the sensible and latent separately and add them together, we can do it in far fewer steps by just taking the mass flow rate times the change in enthalpy, which we picked off of the chart, right, H1 and H2. But we don't know the mass flow rate, we know the volume flow rate. So we'll change mass flow rate to density times volume flow rate times H1 minus H2. And the psychrometric chart doesn't give us the density directly, it gives us the reciprocal of that, which is the specific volume. So we'll make that volume flow rate over a specific volume, and we're going to choose V1 for reasons that we just explained, times H1 minus H2. And now we can substitute in for that, and it's 1,000 CFM. Let's write it out, cubic feet per minute, so we can see all the units cancel. We're going to need to go from minutes to hours, so let's multiply by 60 minutes. And then V1 from above is 13.76 cubic feet per pound. And the difference between H1 and H2 is 28.74 minus 22.01. And that's units of BTU per pound. So cubic feet cancels, minutes cancels, and pounds cancels. So we end up with BTU per hour. And we get 29,364 BTU per hour. So that's the total cooling load. Now, if you incorrectly use V2, and now I'm switching colors so that if you refer to the red, you'll know it's not what you're meant to do. Let's see how those numbers would change around. And I'll skip the units because a lot of the numbers are the same. You'll get a total cooling load of 1,000 times 60, but instead of 13.76, now it's 13.19, and the enthalpy is the same, 28.74 minus 22.01. That equals 30,614 BTUs per hour, which is 4.3% high, which is driven entirely by the difference in those specific volumes. 13.76 is 4.3% more than 13.19, so it drives the total cooling down. And that's how you get the correct answer. When you have the smaller specific volume of state 2, after the cooling, you end up calculating a cooling that's 4.3% too high. So is that a tolerable amount of error? Probably not. A lot of engineering problems you can get away with 5 or 10%, but there's a good chance that that'll be enough to throw you off and pick a wrong answer. All right, let's see what happens in the next one. Now we'll just look at the sensible cooling. So first of all, let's go to our rule of thumb, since that's the first thing most people go for, and see how that holds up. So our rule of thumb, as you are probably familiar with, is Q dot S, sensible cooling, equals 1.08 CFM delta T. So that being the case, we'll get 1.08 times 1,000 for this problem. And the delta T, this is just dry bulb temperature, 76 minus 55. And that gives us 22,680 BTUs per hour. Okay, so that may or may not be a reasonable answer. Let's do it more precisely by using the specific volume of the entering air, V1. So if we're being more rigorous, sensible cooling would be calculated by m dot Cp delta T. And again, instead of density, we'll use specific volume. So that becomes V dot over V1 times Cp delta T. So now substituting in 1,000 CFM, minutes to hours, 13.76 for V1, 0.24 BTU per pound degree Fahrenheit is the specific heat capacity of air. And by the way, in case you're wondering, this does vary with temperature as well, but it's very slight, so you don't have to worry about this changing significantly, at least not enough to throw off the answer to any test questions. And then the delta T is the same, 76 degrees Fahrenheit minus 55 degrees Fahrenheit. And we can go through and cancel some units. We get 21,977 BTUs per hour. So the rule of thumb then, this 22,680, was 3.2% high. So not as bad as when the wrong specific volume was used, but still a few percent off. So take that for what it's worth. And now what about using V2? Again, you shouldn't use V2, but suppose that you did. And I'll skip to the numbers. 1,000, 60, 13.19 now, 0.24, and that delta T is still going to be 76 minus 55. So some of you may be predicting the answer here. 22,986 is 4.3% higher than the correct answer, 21,977. And that's not surprising because when we did the total cooling, V2 caused us to be 4.3% high. And now we're doing the sensible cooling, and V2 again has caused us to be 4.3% high because the error is entirely driven by the specific volume. And I think it's worth noting that at least in this case, the rule of thumb also had some error associated with it, but it had less than you would have if you used V2. And now the last piece of this is the sensible heat ratio. So let's first look at the case where we use V1, which was the correct choice throughout the problem. We'll just take the sensible cooling and the total cooling that we calculated at each point. We got 21,977. I'll skip the units since they're the same. Over 29,346, which is 0.749. So that's the correct answer. Right around 75% sensible heat ratio. Now, what if you use V1 for the total cooling, and then you use the rule of thumb 1.08 CFM delta T for the sensible cooling component? So this is the correct approach, and I'm going to argue that this approach is okay, but not necessarily as accurate as it could be. So in that case, we would get a sensible heat ratio of, let's go to our rule of thumb, 22,860 over the same denominator, 29,346. And that gives us a sensible heat ratio of 0.773. So it slightly overstates the fraction of the total cooling, which is sensible. So that's 3.2% high. And that's a familiar number because we said earlier, when we used the rule of thumb in the first place, we were 3.2% high on the sensible cooling. So that error has just propagated through here to the sensible heat ratio. And now if we use V2 for both the sensible and total cooling, then we calculate a sensible heat ratio of 22,926 over 3614, which equals 0.749, which is exactly the same as the correct answer. So surprise, surprise, even though the wrong specific volume was used, and there are errors inherent in both the sensible cooling and the total cooling, because the same error was made, the ratio ends up being correct because the specific volume drops out of the calculation and the error actually cancels. And now this should be a little troubling because that means you can do some things wrong and still get the right answer without ever knowing that you're making a mistake. And that's really why I wanted to go through this in detail, because I think it's important to do enough example problems and see things backwards and forwards enough times that you realize when you're getting away with something versus when your mistake is actually expressed and shows up, and obviously you learn from it. So the takeaway here is to use the specific volume of the entering air in all cases where you have air flowing over a coil. And then the other part is regarding the rule of thumb and what it actually means to use 1.08 CFM delta T. So as a reminder, I've talked about this in other videos, but since it comes up so often, what's baked into this 1.08 is the 60 minutes per hour and the density of air at a particular temperature, which is arbitrary, of 0.075 pounds per cubic foot, and the specific heat capacity of air, 0.24, which is relatively unchanging with temperature. And since we don't usually talk about density, and since we can't pick it off the psychrometric chart, we usually talk about specific volume, we can rearrange this and show it as 1 over the density. What is the reciprocal of 0.075? It's 13.33 cubic feet per pound of dry air. So if your entering air condition just happens to be on the line of constant specific volume of 13.33, then the rule of thumb will be spot on. Well, where is that line? Let's jump back over to our psych chart. Here's 13, 13.1, 13.2, 13.3, so it's somewhere a little bit past there. This line is a line of constant specific volume, 13.33 cubic feet per pound of dry air. But in the example that I came up with, and again that was arbitrary, the entering air condition was way over here and had a specific volume of more than 13.7. And it's the distance between that line and the 13.33 line that's introducing that error. So if you really want to be precise, have to take the specific volume at the entering condition. On the other hand, if it so happens that your entering condition is at this line or near this line, then you can get away with it. I just wanted to shed some light on this, and hopefully this has been helpful, and now you're able to be aware of what your inlet conditions are and at least make a conscious choice before you take a shot at a problem and end up having error without realizing it. So that's it for this week. If you have a question and you want to submit it for a future question of the week, send me an email at dan@mechanicalpeexamprep.com. It's been an incredible year, and I'm excited for the hundreds of candidates that are preparing for the PE exam, and I'm looking forward to answering any other questions that you may have. I'll see you in the next video.